Hey, welcome back. In this video, we're going to talk about complex numbers. So far in your algebraic work, you've probably almost only dealt with real numbers. It's really important for us to talk a little bit about complex numbers and how to work with them in order to reach the fundamental theorem of algebra. To start the conversation, we have to define the imaginary number. So first of all, an imaginary number is a number that's a real multiple of I, which we define as the square root of -1. Importantly, what I allows us to do, it allows us to work with situations where we have negatives under square roots. A really important consequence of this definition, again, we're defining I as the square root of -1, is what I squared means. So really important, and you'll see this as we do our work here, that I being equal to the square root of -1 is the equivalent to the statement of I squared equaling -1. So another way of thinking about what I represents, I is the number mathematically that when you square it, you get out -1. And depending on your previous experience, you might be thinking, where did this I come from? What is this? And importantly, just like pi or e, for instance, this is a mathematically defined number. I will no longer be a variable, though you'll see it as we work with it. We can treat it as we would with x or any other variable when working with these. But I is not a variable. It's defined as the square root of -1, or again, in other words, that I squared equals -1. So then building off of the idea of I, we can define a complex number. So a complex number is a number that can be written as, we'll say Z represents a complex number here, can be written as A plus BI. So importantly, this conversation, a complex number is this two-term expression. The A and the B in this case, and I'll write this out, are real numbers. They have to be real numbers, but we're including this imaginary part right here. And importantly, when you talk about complex numbers, we always think about it in terms of the real part and the imaginary part. So a complex number takes this idea, but then adds some real part to it. This A right here is called the real part of a complex number. And the B, the coefficient here times the I, the B is called the imaginary part. And just to emphasize this real fast, is that when you write a complex number, it will always have these two terms, a real part and a complex part. That is, unless A or B is 0. So just remind us that complex numbers are written in this two-term form. And we often use a Z as a very common variable that we'll use to represent that. So Z is one complex number, but it always has these two distinct pieces. So that's the introduction to the definition of a complex numbers with the imaginary part. Now we just need to go and talk about how do we deal with these. Basically the arithmetic. If we're multiplying, adding, subtracting, dividing these complex numbers, how do we deal with that? So first we'll tackle addition. In fact, addition is really straightforward for complex numbers. We just use that concept of adding like terms. So in this case right here, we're adding two different complex numbers. When we're adding them, we actually don't need these parentheses, though I usually represent complex numbers in parentheses, just so I have the idea of like this is one number, one complex number, and to make sure I use distribution correctly because we have these multiple terms. But in this case right here, if I'm adding these, it's as simple as adding like terms. The 6 and the 10 add together, so I'm adding the real parts to get 16. I then add these complex pieces, specifically the coefficients, -4 and a +7, give me a +3i. Subtraction is really exactly the same. The only thing we need to make sure of is that we distribute this negative to both of these terms. So what I'll have then is this 6 minus 4i, and then when I distribute this negative, I'm going to write this as plus -10 minus 7i. Importantly here again, I like to write these with parentheses just so I can always think about the interaction of these complex numbers and to not make any mistakes as problems get more complicated. But in this case now, I've distributed the negative. I'm now thinking about addition. This is now exactly the same logic I used up here. Combining like terms to be a +6, -10. The real parts give me a -4, and then I have a -4i, -7i to get -11i. And then with complex numbers, the real fun starts with multiplication. So in this first example I'll do right here, this is a complex number that has a 0 as a real part, so just 5i. So it really only has, the only non-zero part is that imaginary part. So this complex number times this one. And the beauty, again, as previously, we can just think about these in the same operations as our polynomials. I'm going to distribute this 5i to both of these terms. When I do that, I'll get 15i, and then here I get 40, so minus 40i squared. An important thing to state right now is that we expect that when we add, subtract, multiply, or divide two complex numbers, that we end up with a complex number. And in this case, we have what is pretty clear an imaginary part, this 15i, but how do we deal with the I squares? Well, the beautiful thing is we've already defined what I squared is equal to. So I squared is equal to -1. So this statement actually would turn into 15i minus 40 times -1. Again, this I squared being that -1. And the real effect that you'll see, and I'll do this in the next example kind of a little quicker, is that I squared only represents this idea of a factor of -1. So I'm going to rewrite this as a positive 40. I'm going to write this first because we like writing the real part of a complex number first. So this becomes a positive 40 plus 15i. So again, what we just did right there is we multiplied two complex numbers and ended up with a complex result, which we would expect. And we won't go into it in this video or in these discussions, but powers of I, you can have large powers of I, and the only outputs you end up getting are I, -1, or 1. It's the cyclic nature of the powers of I, which you can look up on online resources, but importantly for how we'll be using them in our discussion is that I squared equals -1. If you ever see an I squared, it's a factor of -1, which changes the sign of the term. And then finally, one more example, because it will be important for future work that we're going to do with polynomials, is here I'm multiplying two complex numbers, but in this case, these numbers are called complex conjugates. So we call these conjugates like we do with polynomial conjugates because they have two terms and the only difference is the sign, in this case, of the imaginary part. So importantly, complex conjugates are two complex numbers that have identical real parts. The only difference between the imaginary part is the sign. We have a -5i and a positive 5i here. And importantly, why these are a special case is because of this difference of squares formula, or if written as that, we can write this as the multiplication of conjugates. We know any two mathematical structures that are a plus b times a minus b, it always results in a squared minus b squared. And why this holds an important part when working with polynomials are twofold. First of all, when we multiply any two complex conjugates, and you'll see with this example, is the result is a real number. That's really important. When we multiply these together, we get a number like 35 or 72 without the I part, and you'll see why. It's because of this structure right here. And second is that when we end up finding complex zeros of our polynomials, if we get zeros that are complex, that's where this is leading, by the way, they will always come in conjugate pairs. And while we could employ that equation I just had right here, which is the multiplication of conjugates or the difference of squares, what I'm instead going to do is just multiply this out and we'll verify that formula again. But we get 3 times 3, which is 9. 3 times -5i is -15i. We get 5i. Positive 5i times 3 is a plus 15i. This is that middle term canceling it out. And then positive 5i times -5i is -25i squared. We get the canceling of these I terms, and what we end up getting is 9 minus 25i squared. But this term, we know the I squared makes this simply a plus 25. Giving us 34. And just to highlight it to make sure it's obvious, is that when we multiply these together, this 3 plus 5i times 3 minus 5i, what we ended up with was this 3 squared minus the 5i squared. The thing about there being that I squared in these terms, though, is that I squared represents just a change of sign for that term, giving us a 9 plus 25 being the result of this multiplication. And as I said earlier, the result of the multiplication of these two conjugate numbers gives us a very real number of 34.